So in this example, we start with a table of values for different processes. For these different processes, we're told the energy added via heat transfer, the work done by the system, the total energy at state 1 and state 2, as well as the change in total energy. And we're asked to find in all of these missing entries. This problem, or this part of the problem, will involve the first law. You can see that all of these terms in the first row here involve quantities found in the first law. So let's write out the first law. So the change in total energy of the system is equal to the energy added via heat transfer minus the work done by the system on the surroundings. And the change in total energy will just be the final total energy minus the initial total energy. So let's just do process A really quickly here. Here we're told the heat going into the system is a plus 50. These all have the same units. We're told in the problem statement that each entry has the same energy unit, so we're not going to worry about the units here. But we're told that that's plus 50. We're also told E1 is minus 20, and that the delta E as a whole is plus 70. So to find E2, what we can do, so we're trying to fill in that entry, we know that we have E2 minus E1 is equal to plus 70, where E1 is minus 20, so minus and minus gives you a positive here. When you bring it to the other side, it'll be a minus, so that means E2 must be a plus 50. So all I'm doing is just dealing with delta E is equal to E2 minus E1, and then just solving for E2. So that'll be a plus 50. And then I have, to find the work, I can just solve this equation. So I have plus 70 here, plus 50 here. Bring that to the other side, it'll be a plus 20, but throw the minus in there, so it'll be a minus 20 for that one. Okay, so that seems pretty straightforward. We do the same thing for the rest of the processes. Oops. We do the same thing for the rest of these processes. It's all just manipulations of the first law, this expression here. So let me erase some of the quantities that we put in here. Okay, so let's do process B. We're told that the work done by the system is a plus 20, so that means this is a plus 20. We're told E2 is a plus 50. We're told delta E is a plus 30. So let's solve for E1 in this case. So we have plus 30 is equal to plus 50 minus E1. So if I bring this 50 to the other side, that'll be a minus 20. And so that means E1 is equal to plus 20 in that case. So again, to find E1, I'm just solving delta E is equal to E2 minus E1. To find the Q in this case, I have plus 30 here, a minus 20. So when I bring that over, the Q should just be equal to plus 50. Okay, so hopefully you get the idea. I don't think I'll go through all of the different steps, but they're all just variations on the same theme. It's just a matter of manipulating the first law for all these different cases. So let me just give you the results for the other cases rather than working all of them out. For process C, the delta E will end up being plus 20. The Q into the system will be minus 40. For process D, the E2 in that case will be plus 50. And the work done by the system will be minus 40. And then finally for process E, the delta E will be minus 100. And then the E1 will be plus 20. So for that process E, let me just work out process E since that one's just a little bit different. So for process E, we're given that Q is plus 50. We're given the work done by the system is plus 150. So you can see quickly we have 50 minus 150, so the delta E will have to be the minus 100. And now that we know this is equal to minus 100, we also know E2 is minus 80. So minus 80, it should be a minus 20, will give you a minus 100, and so that's where the 20 comes from. Okay, so hopefully all that makes sense to you, just manipulating the first law. Let's go on to part 2. So we're told that a gas is contained within a piston cylinder assembly, and it undergoes two processes. So let's just quickly sketch this out. So here's our cylinder, piston. We have some gas in here. The gas is going to be our system here. We're interested in how the gas interacts with the surroundings. There is, so the gas undergoes two processes, A and B, between the same end states 1 and 2, where we're given the initial state as well as the final state. Process A is a constant volume process from state 1 to a pressure of 10 bar, followed by a constant pressure process. You know what, let's sketch this out on a PV diagram just so we can visualize it a little better. So here's pressure, volume, and we're told that the initial pressure is 1 bar and 1 cubic meter, and the final pressure is 10 bar and 0.1 cubic meter. So that means state 1 would be somewhere here. So this is 1 bar. Absolute pressure in V1 is 1 cubic meter. And then P2 is 10 bars, so that's somewhere up here. In V2, we're told is 0.1 cubic meter. So that's what our two different end states look like. And so for process A, it's a constant volume process from state 1 to a pressure of 10 bar. So it's going to go up this way to that point, followed by a constant pressure process to state 2. So then it'll go that way. So that's our process A. Process B, we're told we go from 1 to 2 using this PV equals a constant relation. That's called a polytropic process, where you have P times the volume raised to some power. In this case, the power would just be 1. Is equal to a constant. So let me sketch that one out. I'll use a different color. So that'll look something like that. So this is process B. And we're told that kinetic and potential energy effects can be ignored, and then for each of the processes A and B, sketch the process on a PV diagram. Well, we just did that, so that part's done. Evaluate the work and the heat transfer. Okay, so let me go back to my energy flow diagram over here. So we've got some heat coming into and some work being done by the gas on the surroundings. So we're going to try to find that work and find that heat transfer. Okay, so let's do the work part first. And we're going to do process A initially. So this will be PDV work because we're dealing with a gas that's expanding against a piston, so it's, there's some pressure that the gas is applying to the piston, and it pushes the piston, so it's PDV work. So that'll be the integral of PDV as we go from some initial volume to some final volume. And let me put an intermediate point here. Let's call this point 1 prime right here. So I'm going to break this up into parts. So instead of going from V1 to V2, I'm going to go from V1 to V1 prime, and then add in the PDV work from V1 prime to V2. Just because I'm taking two different paths there, so I'm just breaking it up so I can do it using the two different paths. Now the first integral here is actually pretty easy, because if you look at V1 and V1 prime, they're the same volume, right? It's a constant volume process, so V1 and V1 prime are the same, so this integral just becomes 0. If the volume doesn't change, then there is no PDV work. Now, in going from point 1 prime to 2, that's a constant pressure process, so I can pull that pressure outside the integral. So that'll just be the integral from V1 prime to V2 of dV, where the pressure I just pulled outside. I pulled the pressure outside that integral, right? So this will just be P times V2 minus V1 prime. So we know the values for these, right? This is 10 bar. V2 is the 0.1 cubic meter. V1 prime is 1 cubic meter. So when you work out these numbers, the work done by the gas following process A comes out to be minus 900 kilojoules. Now the fact that it's negative means that instead of the gas doing work on the surroundings are actually doing work on the gas. So that means that the piston is actually moving downward. It's doing work on the gas, which makes sense because the volume is initially large and then it becomes a small value. So it means that we're compressing the gas. I mean, the piston comes down. So the surroundings are doing work on the gas. That's, again, why we have the negative here. Now to find the heat transfer for this process, we'll make use of the first law. The first law involves heat transfer, so that makes sense to use that as a tool to figure out what the heat transfer value would be. So we can plug in for our work done by the gas. We know that's minus 900 kilojoules. We're trying to solve for the energy added via heat transfer, so that's what we're going to try to solve for. The change in the total energy is equal to the change in the internal energy plus the change in kinetic energy plus the change in potential energy. But we're told in the problem statement that the change in kinetic and potential energies are both zero. And so what we're left with is just the change in the internal energy, which would be like U2 minus U1. Right? Now, we don't have to worry about putting in the 0.1 prime in here or anything, because unlike work and heat transfer, the internal energy is actually a property. It only depends on the endpoints. It doesn't matter what, we could take some crazy path to go from 1 to 2, but U2 and U1 will still just have the same values. They're just properties that only depend on the current state. They don't depend on the path. Q and W depend on the path that you take from 1 to 2, but not the property internal energy. So U1 and U2 we were given in the problem statement. U1 is 400 kilojoules and U2 is 450. So let's write those in. So this is 450 and U1 is 400 kilojoules. So now we can solve for Q into for process A. And when you work out those numbers, let's see, I did work those out somewhere here. It comes out to be minus 850 kilojoules. All right, so that's what we get for the heat transfer for process A. Now let's do process B. Now in that case, to find the work done by the gas, it'll still be PDV work, but in this case, I know how the pressure is related to volume. In fact, let me write that down here. So I know the pressure is some constant divided by the volume. Now to find that constant, I can just make use of my initial or final state. I'll just use the initial state, but I know that I can use P1 V1 is equal to a constant. So this would be the same as like P1 V1 all over V. Because I'm just using this expression with the initial state P1 V1 to find the constant. So I just substituted in for that. So now let me evaluate the PDV work, making use of that. So this is the work done by the gas for process B. Still PDV work as we go from the initial volume to the final volume. I'm going to substitute in for the pressure. That'd be P1 V1 all over V, because we're given that we're dealing with this polytropic process. P1 and V1 are just constants, so they come outside the integral. So we're left with the integral of dV over V. Well, that's just a natural log, and so what that will be P1 V1 times the natural log of V2 all over V1. And we know all the values for these, right? We're given what P1, V1, and V2 are. Those are all given up here in the problem statement, right up in here. So we can plug the numbers in there and work it all out. And when we do that, we'll get the work done by the gas for process B. That'll come out to be minus 230 kilojoules when we plug in all the numbers. Okay, so that's what we get for process B. Now to find the heat transfer for process B, we still make use of the first law given right here. We still can neglect changes in kinetic and potential energy. So we're just have the internal energy here. The work now, instead of being minus 900 kilojoules, will actually be minus 230 kilojoules. So that's what we'd use up here instead. The U2 and U1 are the exact same values because the internal energies or properties, they don't depend on the path. So as long as state 1 and state 2 are the same, it's the same internal energies. So we can then solve for the Q into the gas for process B, that comes out to be minus 180 kilojoules. So you can see that the heat transfer for process B and the heat transfer for process A are different, and it's because it's path dependent. The works are different and the heat transfers are different because they're path dependent. The internal energies are the same because that's a property and it only depends on the endpoints, it only depends on the states. Now in both of these cases you see that the Q's are negative, so instead of heat going into the control volume or into the gas, there's actually heat leaving the gas into the surroundings. Okay, I think we've covered everything we need for this particular example, so we're going to end it there.